Adam is, I'm just going to go straight through it, and it'll take probably 10 minutes, and then we will introduce the next chapter, chapter 18. I went straight to 19 for some reason. That's what I kind of prepared, and then I went, oh, wait a minute. I want to get to magnetism, but we got to do a circuit first. You do have a new, let me calm down, been running around. You do have a new homework assignment. I only gave you 5 problems. Now, the drawback to them, and they're due a week from tomorrow, so that if there's any questions like on Monday, after we meet again on Monday after we finish the circuits thing, we can solve wrapping those up. All right, and so there's only like 5 questions from chapter 18 because I want to move on. I want to get us to magnetism, which is really kind of cool stuff. And this semester gets easier the further along we go. It does. E&M gets easier. Well, we get out of E&M. That's the nice thing. We get out of E&M and we get into optics and all that kind of stuff. E&M is electricity and magnetism. Okay, so question 1 should have been E. An atom becomes positive ion, and atom B becomes the negative ion. I'm going to turn on the lights. Let me mood lighting here, and I can't see what the heck this thing's saying. All right. Okay. 2 charged particles. All right. Now here. Oh no, I want to leave this off because I want to do this. All right. Here we go. 2 charged particles. Now, this is Coulomb's law. All right. A lot of people miss this, and when I put up the right answer, they go, "Oh, well, yeah." So here we go. Where the heck is the lamps? Turn the lamps on. There we go. That's a little better. All right. So if I've got Coulomb's law, if I've got F equals K times Q1 times Q2 over R squared, and I leave the R the same, and the K, of course, is a constant, but I double both these charges, I get 2Q, 2Q. What happens to it? Quadruples. That's why I didn't double. Slow down, breathe after each question, okay? And then actually go, oh, that's the first thing. Actually write out the formula and we'll see. Okay. A sphere carries a net charge, and sphere B is neutral. They are placed near each other on this insulated table. There is an attractive force between them. D is the correct answer, because just like the balloon, if I make the balloon negative, hold it close to the wall, what happens to the wall? It ionizes itself, right? The positive charges kind of come to the surface, and then you can stick to it, stick the balloon to it. That's that idea. So that was D. All right, electric field lines were B. They are, electric field lines are closer together the stronger the field. Okay. All right. Yeah, A and E were just like throwaways. Luckily, nobody picked those. All right. It says so many electrons are placed on a hollow sphere. Now, what do electrons do? Remember the John Travolta guy? When he kicked up the electrons, what happened to those electrons? They dispersed over his body evenly, right? Because if we have a bunch of electrons, in other words, if I try and put a bunch of electrons here together, all scrunched together like this, what are they going to do? They're going to move apart, right? If I throw a proton, 3 protons in there, they're going to all connect and there'll be 0 charge. But okay, so they all uniformly distribute about the sphere's outer surface. And then problem 6, what is the electric field inside a conductor? Inside it, 0. The electric field inside a conductor is 0. It's always 0. And so now I'm going to say something I hope I don't have to come back and say, but Ting and Hal will keep me honest here. Hal, or Ting, on a wire, the electrons move on the outside of the wire, not on the inside, correct? Or do they move all over? Well, that should be a extra credit question, but I'm tired of extra credit, so we're not going to do it. All right, anyway, we ought to look up and see why, or see what it is. I think they move on the outside. Yes, Stacy. 6 is inside B. There is no electric field in the block's interior. Okay? Electric field on the inside is 0. All right, so 7. To be more effective, how should one shape a lightning rod? Make it all nice and pointy, right? Okay, because that will give you more of those negative charges up there, and the field will be stronger and will attract those positive ions from the cloud. Okay? A conductor is placed in an electric field under electrostatic conditions. Which of the following statements is correct for the situation? This is one where you got to breathe, stop, and just don't go, oh, the electric field on the surface is perpendicular to the surface. Yeah, that's right. A lot of you put A, and I know what you did. You put down A and kept going. You didn't read the rest of them. Read them all. And then when you read them all, you go, oh, all these answers apply. Okay? Okay, and just for your own MCAT reference, I think I've told you this before, never pick not enough information given on any problem, any kind of multiple choice test you ever do. Never ever pick that. That will be wrong almost every time. Now watch the next test I give. That'll be the right answer. Oh, I'll try not to do that. Okay. All right, now this one, question 9 was dirty pool. All right, I admit, this one was mean, because here's the deal. All right, on question 9, I know what all of you did. You went, okay, the magnetic flux, or the electric flux, we're talking about magnetic flux, the electric flux is equal to the electric field times A. So if I make that A 9 times bigger, then obviously my flux is 9 times bigger. What else does this equal? It equals the Q enclosed, all the charge enclosed, which hasn't changed, all the charge enclosed, which hasn't changed, over that permittivity of free space. So, this stays constant. This doesn't change. So if I increase this by 9 way out there, what happened to my electric field though? It's gone down by a factor of 9. So it cancels each other out, so it's the same. Okay? Yeah, you can throw things later. All right? Right, that was kind of, so the answer to that one is D. Okay. All right. Okay, so now the absolute potential at the center of the square is 3 volts. When the charge of plus Q is located at one of the square's corners, what is the absolute potential at the square's center? Okay. Oh, yeah, that would be 0, right, when negative, because here's what happens. Here's the positive Q, here's the negative, right here at the center, same distance. You just add up the 2 potentials going through there, and one would be KQ over R plus negative KQ over R. That equals 0. Okay. All right. An equal potential surface must be, that answer is perpendicular to the electric field at any point. That was your lab. Remember when you're punching on the thing so you could find, in other words, you're finding the potential lines so that you could draw the electric field lines, okay, which were perpendicular. All right. 12, for a proton moving in the direction of the electric field. All right, this one is confusing too, okay, for a proton. First of all, as it moves away from its group of protons, if it's moving in the direction of the electric field, all right, here's what we got. I've got this E field over here, okay. Well, let's just draw it. I've got a bunch of positive charges probably hanging out over here, okay. Got a bunch of positive charges which are creating an E field which are going this way. All right, it's going out all over the place. But as this proton moves away, as this little proton moves along here, he's getting further away from this thing. So therefore, his R is increasing, so his potential is decreasing, and at the same time, his electric potential is decreasing. It's just like if I take this pen, I have it here. It's got a gravitational potential energy, right? And when I drop it, it loses its gravitational potential, but what's it gain? Kinetic energy, right? And so that's what this guy's gaining. He's gaining that kinetic energy, which we had a few problems on when we actually get to the to working out the problems here. Okay, so that one, the answer was its potential energy decreases and its electric potential decreases. Okay, which of the following will increase the capacitance of a parallel plate capacitor? One is if you increase the area, okay, so that, because we put more charge on there, and if you close the distance between the two, because that will drop the voltage will go down, and if Q equals C over V equals CV, and C equals Q over V, as those things get closer, V goes down, make the plates bigger, Q goes up, therefore C increases. So yeah, that answer would be C. All right, 14. Oh, this one was dirty pool. This answer was B. Okay? This answer was B. Because it's the energy, and I'll be honest, I've got to look up the equation here real quick, otherwise I'll get into trouble.
You wrote it at the top of my paper.
I did? Oh, that's good. That was great. Okay, thank you. All right. So some people got the advantage. Okay, so U, thank you, Bethany. All right, so U is equal to 8C. All right, so the original U is equal to C times V squared, right? 1/2 V squared. Right? Hold on a second. So if we increase this by 8, basically what we're going to do is increase this by 8C, and then this becomes over 1/4 V squared, and so therefore it just becomes 2CV squared. Okay. All right. So that one came out to be 2. All right. Okay, a device that produces, this was supposed to be kind of a gimme, a device that transfers chemical energy into electric energy. It's a battery, right? It's a battery. And if I take a 6-volt battery and stack it on top of a bunch of 6-volt batteries, what do I get? If it's 3 of them, I get how many volts? 18, right? But if I take a regular 9-volt battery with the screws on it, and I hook it up in parallel, then the voltage that's going in parallel, which is the next question, would stay the same. All right, next one is just good old Ohm's law. V equals IR, so the resistance, R equals V over I. Right, and I think some of you picked B because you were thinking of but they don't give you the right equation for that. All right, now, when you get your electric bill, what is it in? Y'all know? We talked about it. It's in kilowatt hours, which is power times time, which power times time will give you an energy. So you're buying energy, okay? Voltage is what, yeah, some of you put down, because you think of the power company, so you think you're buying power. Some of you put, I got everything on that. Some of you think that voltage is coming into the house, so therefore I'm buying voltage. No, you're paying for your energy. Okay? Yeah, the answer on that is D. Okay, appliances in the U.S. are designed to work between 110 and 120. The answer on this one is C. Whereas the appliances in Europe are 220 to 240. What would happen if you tried to use a European electric shaver in this country? Well, first of all, it's used to a big V equals I times R. Okay? All right, so now, in other words, it'll have the same resistance. But, so its current is big V over R. Okay, and now, is equal to its I here. And so now, if you got V, you've got this little v coming in, which is the US thing, which is this big V over R times R. It's not going to be able to. It's not going to be able to push that charge. Okay, it requires weight. It won't get the amperage that it needs to operate. All right. So that one was, it barely worked. C. Okay, yeah.
I got that one right and you counted it wrong.
Okay, bring it to me, and we'll change it. We'll change it. Yours might have been the first one I graded. Yes? Yeah.
Going back to number 14.
Yeah.
If you have the voltage, why doesn't, since voltage is squared, I mean, shouldn't they essentially be the same?
Okay, let me work it out real quick for you. I had it kind of scratched out on Brittany's paper, or Bethany's paper, just one. God damn it! Where's the? I mean, shoot. Where is the energy? Where are my equations? How come this chapter isn't laid out like the others? Hold on 1 second. Oh, this is in chapter 16. This is chapter 16 stuff. Because it's capacitance, right? Yes. Yay, team. All right. Okay. Here you go. Here we go. All right. So if here's the deal. If you got UC is equal, this is a good question, yeah, because I kind of went through. UC equals 1/2. The energy equals 1/2 QV, which equals also 1/2 CV squared. Okay, equals 1/2 CV squared. All right. So now then, what we're going to do is we're going to take this 1/2 out. Take this 1/2 out, and we took 8 times. We took 8 times the capacitance, okay, times the voltage we halved. So V squared would be 1/4 V squared. So now I've got 1/2. The new thing, the new energy is 1/2 of 2CV squared. Okay. Right, okay, yeah, so you get 1/2 C, so you get CV squared. This one is 1/2 CV squared. It's doubled. Okay? If you want, I didn't finish the multiplication, but if you go ahead and, you see that now? Because here's the thing, if it's just regular C and V squared, it's 1/2 CV squared. So I did the work in here and I wind up with 2V squared, then I multiply it by the half, then I wind up with CV squared, so it's twice as big. It's doubled. Good question, though. Thank you for making me do that. That was worthwhile. All right, now. Okay. Now, I'm going to spend just a short amount of time. Well, shoot. We might as well go through the whole thing. And, all right. Electron is placed. Now, remember, on problem 1, it was this. Problem 1 was just this. F equals Q times E. Okay? Whoa. I'm having diffraction problems with my bifocals here. Q times E, there we go. Alright, so now they gave you Q, which is the electron, or proton, charge of a proton, times the E field. So that gives you the force. What else does force equal? It equals MA. And the mass of a proton is 1.67 times 10 to the negative 27 kilograms. Alright. So this was your answer to the first part, and then the answer to the second part, A is equal to QE over M, and then the final velocity is equal to AT. I got a lot of 1/2 AT squareds. That's a distance thing. Remember? So you take QE over M times the picoseconds that they gave you, and there you go. All right, the next one, you didn't have to worry about the voltage at all. On the next one, because it was actually, that figure was supposed to go with several problems, but I thought this one was good enough. This one is where we have a bunch of capacitors that are lined up like this with the same voltage going across them. These guys are, okay. Now then, we have to figure out the total, if each one of these is 5, okay, first of all, what we do is we've got to figure out these two are in series, and it's in parallel with this one, so we'll do this, find out total capacitance, which actually comes out to be about 7.5. It works out nicely, actually, because these two together is 1/5 plus 1/5, which equals 2/5, which is 5 over 2, 1 over series. So capacitance in series is 5 halves, just with this. Now they're in parallel, so we've got 5 halves plus 5 over 1, which gives me, multiply that by 2, over 2, which gives me 15 over 2 for this capacitance. And then, so I take 2 over, so now I've got 15 over 2 and 5 in series, so I flip those over. I get 2 over 15 plus 1 over 5 equals 1 over series again. And so that's 3 over, well, hold on a second. Multiply this by 3 and 3, and I get 5 over 15, and then flip that over and I get 3. Okay? All right, so that was that one. So you got thrown off by the voltage because you were trying to go, oh, it's CV equals Q, and you're trying to figure out what the charge was. All right, next one. Last but not least, or next two. I don't think there's hardly anybody here that missed problem 2. The only way you missed the second one on this page is you used 1.4 watts instead of 1,400 watts on it. Okay, and then that I think I only took 3 to 5 off for that. So, all right, okay, all right. But anyway, so we won't even look at problem 2. We're gonna do this last one, and then we'll be gone, and I'll take yours back, and we'll fix it. Okay. All right. Now, starting from rest. A proton falls through a potential difference. In other words, it goes through a QV, an energy of QV, which is 1.2 kilovolts, which is 1,200 volts. So a proton, so the energy that it goes through is equal to QV, which is equal to 1.6 times 10 to the negative 19 times 1,200 volts. Okay? All right. Now then, what speed does it acquire? All right, well, QV equals 1/2 mv squared again. Okay, so it equals 2 QV over m square root equals the velocity, little v. That's it. And then, I guess we got time. This means I won't have to prepare a lecture for Wednesday. This is good. Because we'll get through chapter 18 Wednesday and Thursday. It's not that long of a chapter. All right, so that's good. Oh, Wednesday and Friday. All right, so problem 2 is this. Remember, P equals IV and V equals IR. Those are the two things you had to know to do problem 2. So what is the current? So we've got 1,400 watts equals I times 120 volts. Looks like 1,400 watts over 120 volts equals my amps. Whatever that comes out to 10.9 something like that. And then the resistance, you've got V equals I. Now you got I, so V equals IR. Piece of cake. All right. Remainers are restless.